So I'm going to walk you through the formula of the hydrate lab. So it is important that you read through the introduction of the lab that's there so that you can kind of understand what you kind of see. But what a hydrate is, so we're talking about hydrated compounds. So what you see is that sometimes we're going to have compounds that can hydrate, meaning that just the moisture in the air, the ionic compound has the ability to bind with water in the air. But what's interesting is that they're able to do so in very specific ratios. So an example is copper 2 sulfate. So copper 2 sulfate will take on water. So when it doesn't have water, this is called the anhydrous version. Anhydrous means it's dehydrated. And then if we had the hydrated version, we would actually write it like this: copper sulfate dot 5H2O. And this represents the hydrated version, or the hydrate. So what this means is that for every 1 mole of copper 2 sulfate, 5 moles of water are going to attach to the copper 2 sulfate. And that 1 to 5 molar ratio is very specific for copper 2 sulfate. I mentioned to you another compound, and that is nickel 2 chloride. Nickel 2 chloride, this would be the anhydrous version. That means that it doesn't have water attached to it. And then if I was to add water, it would be NiCl2, but this time it's going to be what we call a hexahydrate, because it's going to be a 1 mole to 6 mole ratio between nickel 2 chloride and water. So again, this would be my hydrated version. So since hydrates are pretty straightforward for us to kind of look at, they are used frequently to be able to determine the ratios and the empirical formulas for these particular hydrates. And we use exactly the same ideas that we've been using before, in the effect that since it's a molar ratio, it should be the smallest whole number ratio that we see. So if we look at the data, what we're trying to figure out in the hydrate lab is that we're given a formula for magnesium chloride with a hydrate. We just don't know how many moles of water there is attached to every mole of the magnesium chloride. So what we do know is that, if it's written this way, that for every 1 mole of magnesium chloride, there is N moles of water that's attached to it. So it's very frequent that what we do is we dehydrate the sample in order to be able to determine what its mass is going to be. So if you look at the diagram that's provided, so if you notice, I just inserted a diagram of how we would actually dehydrate the sample. So inside of here, notice we have a crucible. So a crucible is a porcelain container, and we usually put a porcelain cover over it as well. That just keeps it from sputtering. So what we would do first is we would actually take the mass of that crucible plus the cover. Then we would go ahead and we would add the hydrate to that. And then we would go ahead and measure the mass again. So that would be the mass of the whole thing. And then what we would do is we would go and we would heat it. So we would heat it and continuously heat it for a fair amount of time. And then we would have to take it off very carefully. We have to use crucible tongs, let it cool, and then we would bring it to a desiccator. So I'm just going to move it over to the next slide. So this is a desiccator right here. And that within that desiccator, what it allows us to do is there's a solid that's in the bottom. It's usually like a calcium chloride that's anhydrous. And it's used to collect any water that might be in the space within the desiccator. And then once that cools, we're going to measure the mass again. So at this point, we think that we've gotten rid of the water. So that means that it should be the mass of the magnesium chloride without the water plus the crucible. But we're not sure if we got rid of the water. So what we're going to have to do is we're going to take that sample. Once we measure its mass, we're going to put it back on the Bunsen burner, and then we're going to measure its mass again. And so we're going to heat it for another few minutes, and then we're going to measure the mass again. So that should give us the magnesium chloride plus the crucible. And if we notice that there's no difference in mass based on sig figs, then we know that we've gotten rid of all of the water and we have dehydrated the hydrate. If the mass continues to go up, continues to go down, then that means that we did not get rid of all of the water from before. So we're going to keep heating and cooling until we get to a point that we reach a constant mass. And that's important because then at that particular point, now we have gotten rid of all of the water. So if you look at the data table that's supplied here, we're given that specific information. So I'm going to go ahead and clip that little data table off, and I'm going to move it to the next slide. Okay, so now we have the data table. So now we want to look at what information we have. So the first piece of information gives us the mass of the crucible and the cover. So this is going to be an important value because notice that all of the other pieces all contain, whoops, let me get rid of that for a second. I highlighted the wrong one. So we have the crucible and cover, and we have the crucible and cover, and we have the crucible and cover. So all of those samples are going to be important because we're going to have to take that mass away from the masses that we have, okay? So now we look at the other pieces of information. So now we have first heating, second heating, and third heating. So what I want you to notice is that between the first and the second heating, the mass went down by 0.006 grams. So that's not within a tolerance that we're looking at the plus or minus within the sig figs. So now we're going to look at the second to the third heating, and notice that we're only looking at 0.001 grams. Well, since our balance is measuring to the thousandth of a gram, this is a good value within sig figs. So this means that at this particular point, that now we have constant mass, and it means that all of the water is evaporated. So that's an important piece. Okay, so now what we're going to do is we're going to look at the data. So we want to figure out, if you remember, it was MgCl2.NH2O. So we want to figure out what the formula of the hydrate happens to be. So in order to figure that out, we're going to need, so we need the moles of MgCl2, and we need the moles of H2O that are in the sample. So that's what we have to figure out. So in order to figure out both of them, we're going to need to figure out the grams, what the mass is. So if we look at the first one, we have the mass of the crucible and the cover. And then the second part is the mass of the crucible and cover and the hydrated sample. So we're going to look at the hydrated sample first. So the hydrated sample is going to be the mass that we're going to get from here, because this one has to be with water. So that's going to be the 25.825 grams minus the mass of the crucible, which is 22.347 grams. Okay, so that's going to give 3.478 grams, and that again is going to be the hydrated. So that's MgCl2.H2O. So it has all of that. So now we want to figure out what is the mass of the anhydrated sample. So the anhydrated sample well, that's going to be the mass of the constant mass, so that's 23.977 grams minus the mass of the crucible, which was 22.347 grams. So that's going to give us 1.630 grams. Don't forget about sig figs. And the anhydrous sample means that we're talking about just the MgCl2, right? So that gives us the mass of MgCl2. So that gives us that piece. So now we need the mass of the H2O. Well, if we look at this mass here and we subtract this mass here, we're going to get the difference is going to be the water. So we're going to take the MgCl2 H2O mass, which is 3.478 grams, and we're going to subtract from it the mass of just the MgCl2, which is 1.630 grams, and that's going to give us 1.848 grams. So I'm going to go ahead and move those numbers over to the next page. Okay, so from the previous slide, we know that for the MgCl2, we have 1.630 grams, and for the H2O, we have 1.848 grams. So in order to find the smallest whole number ratio, we have to convert them both to moles. So for the magnesium chloride, we know that in 1 mole, there's 95.21 grams, which gives us 0.01712 moles. And then for the water, we're going to take 1.848, and in 1 mole of water, there's 18.02 grams, which gives us 0.10255 moles. So now what we want to do is we want to find the molar ratio. So for MgCl2, we have 0.01712 moles, and for H2O, we have 0.10255 moles. So once again, we're going to look for the smallest whole number ratio. So if we want multiples of, we're going to divide by this lower number. So we get 1 for magnesium chloride, and we get 6. It comes out to be 5.99, so we can round that to 6 for the H2O. So we have, therefore, the formula of the hydrate becomes Mgcl2.6H2O. So that means that it is now what we call magnesium chloride hexahydrate. So the lab continues on with 3 different questions, and I'd like to give those a try so that we can look at those answers in class. This was an AP question that I just turned into a lab example so that we can look at how we determine the formulas of hydrates. So I hope this was helpful, and I will see you in class on Wednesday. No, Thursday. Thursday. Okay, have a great day, everybody.